Hello everyone, and welcome to Tech Talk session number 17, Harmonic Analysis. Knowing the basics is essential. That's the topic of today's presentation. So we're going to go over some housekeeping things first before we get going with the presentation. And Matt, if you can flip over to the PDF. Yes, perfect. Let me get my PowerPoint. Here we go. So, first of all, don't forget to ask questions, and today we have something slightly different than usual. When you ask a question today, we're going to try to answer it as we move along. So Matt will show you exactly what's going to happen. You ask the question, he will narrate the question. Okay, and then also I wanted to put a reminder out there of what NEPSI does. NEPSI is a designer and manufacturer of medium voltage metal closed capacitor banks. So 2.4 kV up through 38 kV, that's what we manufacture. If you have a project that you are engineering, if you're in the early design stages, or if you're ready to purchase even, come to NEPSI for a quote, come to NEPSI for application assistance. We'll help develop that project, whatever it may be. NEPSI ships around the world. Our dominant area is North and South America, but if you got a project in any of these territories and even around the world, please come to us for a quote on harmonic filters or capacitor banks between 2.4 kV and 38 kV. And okay, so today's presentation is about harmonic analysis. I will go through this slide in more detail next week. But this is the steps required to do a harmonic analysis, to perform a harmonic analysis. And normally we are involved with the creation of a system model first. And a lot of times, in most cases, harmonic analysis is done with a program, ETAP, EasyPower, PSCAD. There's a lot of different programs out there that do harmonic analysis. All these programs work about the same. It is my opinion that for you to be involved with harmonic analysis, you need to know the basics. I oftentimes get questions or I get RFQs from people who have done harmonic analysis. They got the tool, the harmonic analysis program, but the output that they are getting from the program or their input is absolutely wrong. And part of this is they do not understand the basics of harmonic analysis. So today's presentation is about doing harmonic analysis, understanding the basics. If you understand the basics, you can pick up these other tools, you can verify the output of those tools, and confirm that that output makes sense. So that's the topic of today. We're going to start with the very basics of a system and develop a one-line diagram from that system and talk about how you make the calculations on paper with a pencil. And if we have time at the end of this presentation, we will actually go through an example. So the steps here, we will go in detail, I think, on part 2 of this presentation and how we develop the system model, where we get the data, how we validate the system model, what impedance scans are. We will be talking a lot about impedance scans today. We'll be talking about how to calculate current and voltage distortion on the system, and that's really one of the key outputs to a harmonic study. And to finally, if you have a harmonics problem, a VTHD problem, a harmonic current distortion problem, anything like that, a resonance issue, what type of filter you would go after and what that design philosophy might be in developing a filter for that project. And finally, we'll talk a little bit about reports. So why perform harmonic analysis? Okay, and one of the key reasons is you're trying to determine compliance with IEEE 519. IEEE 519 determines the current at the point of common coupling and also recommends voltage and voltage distortion standards by the utility. It might be a new facility or you might be an existing facility. You might be adding large drive systems to a project and you need to determine compliance with IEEE 519 or some other standards. Last week, 2 weeks ago, we had BBA on. We talked about Hydro-Quebec. Their standards are slightly different. I will show you today also some standards from Chile. Their standards are also different. So you're doing an analysis to determine your compliance with some type of standard, whether it's IEEE 519, an IEC standard, or a standard in Australia. But the analysis basics basically are the same. So we're going to be talking about the calculation of voltage distortion, current distortion, and we're also going to be talking about resonance, what happens during resonance. When you add capacitor banks to a system, Or say you have a lot of capacitance in a system because of cable capacitance, we're going to be talking about, well, what happens during that resonant condition and how does that impact voltage and current distortion. And next week we will be talking more about filters and how harmonic filters correct power factor, prevent resonance or preclude resonance, and how it can mitigate voltage and current distortion throughout your plant. So let's talk about linear loads and nonlinear loads. This is a concept that's often discussed when it comes to harmonic analysis. So a linear load means that if I were to input a sinusoidal voltage waveform here, that I would get a sinusoidal current flow. So I got a resistive element. If I put a voltage across that element and it's a sinusoidal voltage, I will have a resulting sinusoidal current. So it will have the exact same shape, and that's called a linear load. Examples are incandescent lights, resistive heaters, and even induction motors, for the most part, is a linear load. But nonlinear loads, you may input the blue waveform here, a sinusoidal voltage, and you get a square wave, and that's the red. So we put a sinusoidal voltage across the load, and the current that flows through that load is a square wave or some other shape. And the issue really with harmonic analysis is, how do you do the analysis here? How do you do the analysis? You have a square wave input, and your normal circuit analysis falls apart here because you're putting a sinusoidal voltage in and you get a sinusoidal current. So really, harmonic analysis is being able to do the analysis with these types of loads. And so these types of loads include variable frequency drives, cycle converters, LCI drives, rectifiers, arc furnaces, all these types of devices that have a harmonic current flow associated with sinusoidal voltage input. And they're considered nonlinear loads, but they're loads that produce harmonic currents. And this is the key part, is they produce harmonic currents. So let's just talk about this for a minute. We have a square wave, and the tool that's used to do this analysis is called the Fourier series analysis and Fourier Transform. And really, harmonic analysis on the most fundamental basis is using the Fourier Transform. Do you need to know the Fourier Transform to do harmonic analysis? No, but it's important to at least know a little bit of foundation about what's going on. So this is the square wave that we talked about before, and you can kind of see, maybe you can't see my mouse, this is the square wave, and I could take that square wave and decompose it into a fundamental frequency, the green curve here, and then I can add to that a third harmonic, the blue waveform, and you can see that I have this faint red curve here in the background. That's our original square wave, and the dark red actually represents the summation here. So I can keep adding additional harmonic currents, the fifth harmonic and the seventh harmonic and the ninth harmonic and the 11th harmonic and finally the 13th harmonic. And you can see that if I take all these subcomponents here, okay, I can develop that original square wave that we have. And this is really the basis of harmonic analysis, is we're taking a square wave and we're decomposing it into a bunch of sinusoids. Those sinusoids are multiples of the fundamental frequency. So a second harmonic would be 2 times 60 if it was a 60 hertz fundamental system. Third harmonic would be 3 times 60 or 180 hertz, and so on. So this is the concept of harmonic analysis, is taking that square wave, decomposing it into harmonics. Now, what we can do with these harmonics is we can do normal network analysis again. We can do that same analysis that we did for the linear loads with the nonlinear load, but the difference is that we need to do the analysis for each and every harmonic. We need to do it for the second harmonic, the third harmonic, the fourth harmonic, but the analysis techniques, and it's really Ohm's Law, V equals I times R, and that's what we will show, or V equals I times Z or I times X, depending upon how you look at it. It is really that analysis is what we're talking about here. Ohm's Law, it boils down to something that simple. So One thing is I think important to remember is if we look to the left here, the sinusoids have a phase angle associated with it. So these phase angles are going to shift. Just like at the fundamental frequency, there was a power factor angle. Well, at each and every harmonic, there is a phase angle. And we could have one harmonic producing device producing harmonic current at plus 180 degrees, and we can have a second device producing harmonic current at a minus 180 degrees. And the net result is they would add to zero. So remember that harmonic producing devices produce harmonic currents at various phase angles and also at various angles of magnitude. Each and every device will have a slightly different signature associated with it. The other thing to remember is that most three-phase systems that have triplet harmonics outputs, the out harmonics do not flow in the network. Okay, they are not produced by three-phase devices. They are canceled out within the device itself. There might be a small amount of third harmonic. We'll call that a positive sequence third harmonic. But for the most part, the third harmonics are most often eliminated in harmonic analysis, especially with VFD drives and other similar three-phase devices. So not true for arc furnaces, though. So we'll start off with a very simple system here. And so on the left here, we have a source equivalent, and it's an 8 kA source equivalent. So 8,000 amps source short circuit level with an X over R of 10. And it's got a line to ground fault current. We actually show a line to ground fault current here of 7.5 kA with an X over R of 13. Important thing to know is harmonic analysis, 99% of the time, is a three-phase analysis. So we are not paying attention to ground fault current. It doesn't make a difference in the analysis for the most part. You're not concerned about that. So it's a three-phase analysis. We assumed everything is balanced. And if you recall from your years at college, for those who have studied network analysis, you can take a three-phase circuit and represent it with a single-phase equivalent here. And that's exactly what harmonic analysis is doing. We're taking a three-phase network, which is represented by this one-line diagram, and we're converting it to a single-line diagram as shown there on the right. Coming down the circuit here, it's a 138 kV bus. This is being fed from the utility. We have this thing called point-of-common coupling we'll talk about in a moment. You have a service transformer, in this case is 10 MVA, and it's got a value of 138 kV primary to a 13.8 kV secondary, and then we got a secondary main. And then down here we have a harmonic producing device. Here we're representing it as 3 megawatts and 3 megavars, so like a 0.7 power factor harmonic producing device. This is just arbitrary. We're taking the system, we made it up, and we're showing it here. And then we got some linear loads, more linear loads like the motors themselves. And theoretically speaking, the motors do have a slight amount of harmonic current, but very, very small. It's only when those motors are equipped with a VFD drive or maybe an RVSS, soft starter, that you might have some harmonic producing current there. So we take this circuit here, and the source impedance up here is represented here by a R and an X. So we have R and X, and that's the ZS, that's the source impedance. And we also have a ZT, which is a transformer impedance here, and we're going to assign numbers to this in a moment. And then we have the harmonic producing source here. Now, harmonic analysis almost always assumes that the harmonic producing device is a current injection, an ideal current source, and it's got a current injection associated with it. So in this case, this device here, okay, is producing these harmonic currents: 8.3 amps fifth, 6.0 amps 7th, 3.8 amps 11th. These are values, and we'll talk about where they come from, but these are harmonic current injection values. They're ideal current values, which means that no matter what these impedance values are here, that amount of harmonic current flows, much like a CT secondary if you think about a current transformer. No matter what the primary current is, through the window of the CT, the secondary current is a ratio of that, and it's being injected into the metering devices. In this case, the fifth harmonic would represent 5 times 60, 300 hertz. It'd be 8.3 amps. And no matter what this impedance is, to repeat it again, we would have 8.3 amps. So this harmonic device, this circuit, is just a very simple series circuit. And if you think about calculating, say, voltage distortion at this point here, okay, it would be just the current times the impedance here would equal the voltage there. So it's just Ohm's Law, V equals I times R, or V equals I times X. It's a little bit more complex because we have to deal with all these different harmonics, and we're going to talk about that in a moment. So let's talk about the current injection values first. The current injection values come from the harmonic producing devices, VFD drives, the arc furnaces, cycle converters. You name the nonlinear device, and out there was a signature harmonic current associated with it, a harmonic current injection. Okay, where do you get these values? Well, you can get the values from system measurement. You can send somebody out into the field if it's an existing system, and he can put on a harmonic measurement device, say a fluke, and he can measure the harmonic current on that device and come up with these values. If it's a new system, you might go to the drive supplier and you might ask them, hey, I got this 1,000 horsepower drive. What harmonic currents does it produce? Because you need to model it in your harmonic analysis program, and you would get that data from them. Or you can assume typical data, as we do here. We talk about the typical data, and here we're showing that based upon the pulse number, if it's a 6 pulse or 12 pulse, 6 pulse, 12 pulse, 18 pulse device, it produces different harmonics associated as this formula implies here. There are a lot of different places, through measurement, through talking with the supplier, or through assumed values. And if you just search on the internet, you can find lots of places where you can find that assumed value of current injection. And when you talk about drives, it's important to also note that depending upon the type of VFD drive, you may, and also depending upon the impedance, and here we're showing a transformer, or an impedance up front of the drive, how much impedance or drive isolation transformer impedance is up in front of that drive, will also change the amount of harmonic current flow that you get. So a 2% reactor here, the THD is 52%, while for a 4% reactor it's 35%. And they have high pulse drives, and you have active front end drives, and the distortion values all change. So you can't just assume a harmonic current value. You have to know the type of drive you're dealing with, perhaps talk with that supplier, find out what they have, and come up with a harmonic current injection. So let me get back here. So point of common coupling, this is a term that you often hear, and is in relation to IEEE 519. So IEEE 519 limits the amount of harmonic current flow that you get at the point of common coupling, and it's based upon system voltage level, and we can click here and kind of go into it a little bit. The IEEE 519 has voltage distortion limits at the point of common coupling. So this basically is the metering point by which the utility is supplying the industrial complex with power. So normally it's a metering point, medium voltage point, or high voltage point in a network, and it is a 2014 is a statistical based limits now, and really the one that I often pay attention to is this 95 percentile, meaning 95% of the time the values will be below that value during a measurement period. And that measurement period might be a month or a week, typically a week, and all those measurement values are bucketed into a statistical table, and they look at the 95 percentile number, and it has to be below this table. So this represents voltage distortion limits at the PCC, and this is really what the electric utility should be supplying you as a customer, if you're a customer, wind farm, renewables plant, or an industrial plant, whatever it may be. You can expect that your voltage distortion should remain below these values at the point of common coupling. And really it's based upon the system voltage here. So if your voltage is less than 1 kV, you should be expecting these types of of voltage distortion. So this is individual voltage distortion and total harmonic current distortion here. And at higher voltage levels, and so 1 kV to 69 kV, that would encompass the medium voltage networks that are most common for industrial plants, 2.4 kV up through 38 kV, and then 69 kV would be subtransmission. And then you got these transmission levels. You can see that as you go up in voltage, the distortion that the utility can deliver is less and less. And this includes for both the individual and also the harmonic values. So moving on to current distortion limits. And really the current distortion limits is a limit that's imposed upon the industrial customer. So remember, industrial customers installing drives on their network. Those drives are producing harmonic currents. Those harmonic currents are flowing back through the series network. We'll go back to that equivalent circuit in a second. But they're limited to the amount of harmonic current that can flow into the network. So the drive here is to try to reduce the amount of current distortion each and every industrial customer is sending out into the utility grid, because we're trying to improve power quality for everybody. So it aims to put the responsibility of the industrial customers with nonlinear loads to correct their problems at the load. And that's really the aim of IEEE 519, is to correct the current distortion at the PCC to within certain values. So it's based upon, again, 95 percentile, as we show here. This is the value that I pay attention to the most. And the tables are based upon short circuit level. So in other words, your I short circuit to I load level. And it's also based upon the system voltage, 120 kV to 69 at the PCC for this case. So basically the tables work that you go in based upon the voltage of your PCC and the ratio of your short circuit current to your load current. And that load current is your demand current. Okay, and that might be what you get on your utility bill, for instance. What is the total demand of the plant? And that is what's in the denominator. And the values over here are percentages. All right, so these are individual harmonic percentages. So from the third up to basically the 11th and below, you have this limit of 4% for this short circuit ratio of something less than 20. All right, so you know your demand current based upon your utility bill, and basically saying, well, I can have my current distortion at the PCC to be 4% of that, and that would be a value in amps, okay, amps. And that's really what your harmonic analysis is going to do. You're going to determine the amps, and you're going to compare it to the values that you calculate with this table. On the end here, you have TDD, total demand distortion, and this is 5, 8, 12% TDD, depending upon the short circuit level. So you can kind of see that as the short circuit level goes up, the customer is allowed to inject more and more harmonic current. And that's because the impedance of the network is going down, which means the amount of voltage distortion that's produced by the current that's being injected into it is less and less. And that's why you're allowed to produce or to inject more harmonic currents for systems that have higher short circuit currents, or for what we would call systems that are stiffer, a stiffer system. So the tables repeat themselves. This one is for 69 kV through 161 kV. And you can do the same here for systems greater than 161 kV. So another one that's interesting is we were just asked recently to do a harmonic study in Chile, and to verify a harmonic filter that we were working on down in Chile. And the standards down there, it was desired that we meet both IEEE 519 and that we meet the Chilean standards. And so here you can see in these tables that the IEEE 519 was a more restrictive standard. So it's important to understand where you're doing the study, what are the limits that you're allowed to produce, and that's going to change depending upon the point of common coupling, the utility agreement that you have, the interconnect agreement that you have, and perhaps what country you're in and to what standards you're applying your limits to. So we'll move on with this analysis. So we have this source impedance ZS represented by this short circuit AKA, and we got ZT is a transform impedance here, TX1, harmonic current injection, just to repeat, is coming from here, and that's an arbitrary value that I made up for this presentation. But that data would be something that you would obtain through some type of load study by talking with vendors or by taking measurements and putting that value there. So I assigned impedance data now to this equivalent circuit. And remember, this is in a 60 hertz network, and what I did is I reflected everything to the 13.8 kV system. And I like to work in ohms. You can do this analysis working in per unit. My preference is to work in ohms rather than work in per unit system because I have a feeling for ohms. When you think about 13.8 system, you can think about half an ohm per mile. A transformer, 10 MVA transformer, typically has an impedance of about 1 ohm. So when we talk about ohms, I got a physical feel for what it means. So we can take this equivalent circuit, which now consists of both the ZS, which is 0.1 ohms, and 1.42 ohms for the transformer reactance, and add those together. Remember, this is the R's need to be added together, and the X's need to be added together. So R's 0.01 ohm and 0.07 ohms here. They need to be added together, and then the X's need to be added together separately because it's an impedance, right? One thing that's interesting to note here is that the source impedance is very low, 0.1 ohms compared to the transformer impedance. And this is a key point with harmonic analysis: is the transformer is the lion's share of the impedance here. So when you think about current injection here, okay, it's this current times this impedance creates the voltage here, okay? And the majority of that voltage is produced by the impedance of the source transformer, GT. The source impedance over here is very low. So that transmission level voltage, the impedance associated with it, reflects through the transformer by, I think it's over here, by the turns ratio squared. And do I have it, base impedance? No, I'm calculating it the other way, but this impedance reflects basically through the transformer by the transformer ratio squared. So I think if we were to go back, let me go back this way. We were at 138, so it would be 13.8 squared divided by 138 squared. Okay, so the impedance up here. So it becomes normally very small and oftentimes insignificant, the source impedance. But not always, and this is the case. You have to know when it's insignificant by asking questions or doing the analysis, but oftentimes it's insignificant. So we take those two impedances, ZS and ZT. Remember, I added the R's, I added the X's, and I come up with a single impedance here. And what you have to remember from this point on is that we're talking about inductance. This 1.52 is inductance. And inductance and inductive impedance is equal to 2 pi FL. 2 pi FL, which means that if I double the frequency, I double the reactance. If I triple the frequency, so in other words, the third harmonic, I triple the impedance. And so we have this impedance curve here, harmonic number here versus voltage here, okay? Oh, actually versus ohms, I'm sorry. So it's ohms here and harmonic number here. And if we were to look from here, basically look into the circuit, we would get a straight line, and it's a straight line of ohms versus frequency. And I kind of go back to perhaps, no, kind of got this messed up again. All right, it's here. So I will move my head out of the way just for a quick second. So you have X of L equals 2 pi FL. And for capacitor, remember, as you go up in frequency, the capacitive reactance drops off. And we'll kind of get into that in a moment. So let's move forward. So you get this straight line. So we can calculate the voltage here very easily now, if you think about it. We take this 8.3 amps, we multiply it times 1.52, but because it's the fifth harmonic, it's 5 times 1.52. So 5 times 1.52 times 8.3 will give me the fifth harmonic voltage at this point. I can do the analysis for the seventh, same thing, 7 times 1.52 times 6.0 will give me the 7th harmonic voltage at this point. And you do the analysis for each and every harmonic. So this is the thing with harmonic analysis, and it's one of the reasons to use these harmonic analysis tools, is that it becomes a significant number of calculations. It's like running a load flow, but at each and every frequency. So it's not exactly the same as a load flow, but it's in concept, it's similar to that. So we can calculate THD here, total harmonic distortion, by summing the squares of each of the harmonic currents and divided by the fundamental squared and take the square root. Okay, and we can do the same thing for VTHD. If we calculate the voltage here at each of the harmonics, we can calculate VTHD. So same concept. And then TDD is a total demand distortion, and really in the denominator here, it's the demand current that you have. It's the demand current, what you're reading off your metering device. So what I do is I take these currents. This is our currents here, and I'm going to use this. We have our currents 8.36 and 3.8, and we put them down here on the curve. And basically, so I have 8.3 amps going through that value of impedance, and it results in a certain amount of voltage. And I'm just doing the math here, multiplying those currents times the impedance read off this curve, and I get these values of voltage. So at the 5th harmonic, I'm getting 63 volts. And at the 7th harmonic, I get 64 volts. So this is harmonic analysis in its most basic form. And it's just V equals I times R. I mean, think about it. That's all it is. You just got to know some basic rules. One of the rules is that the reactance goes up with frequency, okay, linearly with frequency, and I get that value of voltage. And in this case, I'm getting a value of VTHD of 1.9%. Obviously, current distortion is easy to calculate. This is a series circuit. There is no splitting there. Okay, so let's talk about what happens now when you add capacitors to the system. And this is really the thing that we see the most. For the most part, when you do harmonic analysis, I'm going to go back. If it's just a straight impedance, very, very often you will not have a harmonics problem. It takes a capacitor or capacitance in a network to really create the problem. And this isn't always the case. You can add a very large drive to a system, and just the impedance of the network alone will cause a high voltage distortion. And that's the other thing I should talk about for a moment is when we're doing harmonic analysis, our desire inside the plant is to limit the voltage distortion to 5%. So I kind of scroll back to this analysis here and here. And we're going to do a harmonic analysis. Our desire is to limit voltage distortion in the plant to 5%. Now, IEEE 519 doesn't dictate that value, but if you're designing for a relatively good standard of power quality, the desire is 5%. So for me, when I do harmonic analysis to come up with a filter design, or if I'm adding capacitors to a network and I want to determine, well, what's my limit, I use 5%. I also look at the current at the point of contact coupling. If the utility is monitoring for IEEE 519, you want to be within those IEEE standards. So that's the two key values I'm looking at: current distortion to PCC and voltage distortion within the plant itself. So let me scroll back ahead. We're adding capacitors to a network here, and you can see here, typically we're adding capacitors in a variable form. And in this case, we just arbitrarily picked a 1 megavar, a 2 megavar, a 3 megavar, and a 4 megavar bank. So it's a multi-stage cap bank, and we can calculate the impedance of that capacitor here very easily, right? It's the voltage squared divided by the megavars. Will give me the ohms of that capacitor. So very easy to calculate. And so let's see how that impacts the model. And so here we have the variable capacitor. We have that same source impedance as before, and we're showing those values of ohms here. And the thing to remember is that over here, the value of X of C, as you go up in frequency, drops off. There is a crossover point by which the red line, which is our original transformer source impedance line, crosses the capacitive reactance line, and that point is called resonance. And you can easily calculate that with this formula here. And it's probably the most popular formula when it comes to harmonic analysis. It's just a back of the envelope type calculation. And really, whenever you're adding capacitors, you should always be thinking about this. Am I going to tune my system to a harmonic produced by the drive systems? 5th, 7th, 11th, 13th. They're really what I would call the pain points. If you calculate resonance at the 5th, 7th, 11th, or 13th, or even near that, you should be thinking, do I want to add capacitors to the network? Am I taking a chance? And we're going to talk more about what happens to that. So remember, this formula is only valid for this system as we have modeled. It's not good for a system that has both primary and secondary capacitor banks. So you say you had transmission or distribution level cap banks, you step into the plant environment, you put another capacitor bank there, and perhaps you go down to the low voltage network and you put another cap bank there. This formula does not work for that. It's for the most basic diagram as we have shown here. Okay, so what happens during resonance? Now, where X of C equals X of L, we have what's called resonance, and basically the impedance has now changed. This red dashed line here is the impedance of the network of that transformer, that original red dashed line that I had previously shown. It's a very low value when you think about it compared to the new curve, the magenta curve. So we added capacitors to the network, and the resulting impedance that we see, okay, that we see here, the impedance that we see looking into the circuit is this magenta curve here. And that's a very high value of impedance. In fact, it's limited basically by this formula here. The peak is equal to X of C, the capacitive reactance, divided by N, N being where the harmonic resonance occurs, divided by the resistance of the network. And remember, resistance of the network is very low. It's the cable resistance, the resistance of the transformer. Typically, those medium voltage transformers have an X over R of maybe 25. So R is a very low value, and thus you get this very high peak in impedance. So if you think about it, if I have current injection, and that's what we're doing here, these are those original current injection values at each and every harmonic. If I multiply those values, 8.3 amps, for instance, at the 5th, and 6 amps at the 7th, multiply that times the impedance curve. Again, we're just doing Ohm's Law here. I get the value of voltage distortion, and that's what we show here. And you can see our voltage distortion now is up at 4.32%. So it's climbed. All we did was add capacitors to the network, and we took the voltage distortion from something that was less than 1% always up to 4.32%. And to some degree, this is okay. This is okay because it meets my limit of 5%. I was talking about meeting the limit of 5%, and we meet that. The issue you got is how well do we really know this resonant point? And this is the risk factors that you have as a designer, is how much do you trust the data? And so let's talk about what happens. You can think about shifting that impedance curve to the left. That's kind of what I just did. I shifted the impedance curve to the left, and kind of go back here. We have the original impedance curve here. The distortions are low, but just think about this. This is about 550 ohms. If I were to shift it to the left, and I could have potentially 5,000 volts of voltage distortion now. So we're in not current injection, 8.3 amps of fifth harmonic current injection. Now we're seeing near 600 ohms of impedance, and it creates this huge voltage distortion. And that's the problem with resonance, is when resonance corresponds to a harmonic, you got an issue. And when I was looking at this system, the issue is we can get this shift. We can easily get this shift back and forth. And this shift can occur for a number of reasons, and that's what we talk about here. The short circuit impedance, and we all know that the short circuit current will rise as we put more motors on the system. So depending upon the number of motors connected to the system, our short circuit current changes. That results in an automatic shift in the curve. A higher short circuit current will shift the curve to the right. And so I kind of go back to here. Higher short circuit current will shift this magenta curve to the right, off the 5th towards the 7th. The weaker the system, the lower the resonant point will go. It will shift to the left. Also, we're adding capacitors in a variable format. As we add capacitors, we're going to walk through resonant points. So this also becomes an issue. The other thing is when you buy capacitors, the standards state 0 to plus 10%, 0 to plus 10%. So we really do not know the exact value of that capacitance. So we put a line through that one too because it's variable. There's a possibility that it could be higher or lower than what you modeled. And then finally you have the impedance of the source. This is the transmission grid. Remember, this is a relatively small value, but it does change. The value does change depending upon local generation. Think about, you have the renewable plants, you got coal plants that come in and out depending upon politics to some degree. Are those coal plants running or not? So depending upon transmission outages, the impedance of the source can easily change. So you have to consider these when you're doing your analysis. Is this acceptable, and how much risk does somebody want to take? When you calculate a resonance at 5.59 here, in my opinion, you're in a zone where you're taking a large risk. And if you purchase a capacitor bank for a system like this and you do have resonance, there's a good chance you got problems. So resonance is definitely an issue. We oftentimes will talk to customers and they will talk about, oh, hey, I have active front-end drives, or I have a high pulse drive. And so I've taken the liberty here to talk about this a little bit. And the notion that the customers tell us is, hey, I have an active front-end drive, I have an 18-pulse drive, and if I have those, I don't have to worry about harmonics. And that statement is actually wrong. It's a wrong statement to make. You still have to worry about harmonics, and we talk about that here. We just go through the examples here, what the distortion can be. So an active front-end drive produces a very low-level harmonic current. Here we can kind of see that they're at 2.2% here for the 18-pulse drive and 3.7 for the 5th, so the harmonic currents are low. They are IEEE 519 compliant. The issue you have is that if the harmonic current from these drives interact with the system and the system has resonance, then you do have a problem. And this is really key. We will oftentimes get customers that say, hey, I got active front-end drives, I don't need to worry about resonance, I don't need to worry about distortion. They're IEEE 519. I'm going to buy a standard cap bank. And this is the wrong statement. For this particular system, if we were to install a 5,000 horsepower drive with an active front end on it, I calculate here that it will put out 3.43 amps at the 5th harmonic, and that 18-pulse drive will produce 5.77 amps a 5th. The resulting voltage distortion will be near 52%, okay, and near 33% for an active front-end drive. So both unacceptable. You can do the same thing for published data from other drive suppliers, and we kind of go through it and show for all the results. For the Siemens device, the harmonic currents were reported as very low, but there are some caveats that have come with their drives. To some degree, those devices under ideal conditions produce very, very low harmonic currents, but there are caveats. If I have imbalances in the system, that can create additional current distortion. If I have voltage distortion, ambient voltage distortion, you can have additional current distortion. So again, you still have to be careful, even when you're purchasing these very high-end drives, what might happen. Let me move on. Okay. So we also talk about tuning around resonance. We hear customers say, well, I have this 5.59 resonance, or I'm going to take some cans out or put some capacitor cans in, and I'm going to shift my resonant point around. And to some degree, this only partially works. Remember, we have this issue of really understanding what the source impedance is, how much short circuit current I have, and this fact that resonance will shift around. But when you look at the impedance, the resonance here, and we kind of showed up here in the top left, the resonance has a certain amount of broadness to it. And I zoom into that down below here. And remember this blue line here, this blue dashed line is our original transform impedance line. I added a capacitor bank here, and I created a resonance at 5.59. You can basically see that I have increasing impedance of the network all in that shaded red area, which results in a higher voltage distortion. So the impact of adding capacitors to a system normally means increasing voltage distortion. And it just so happens, and it's normally bad luck, is that when you do power factor correction in the standard power capacitors, more often than not, the resonance is going to get down into that 5th to 7th range. You're going to get an impedance curve that looks like this. The net result is you're going to have an increase in voltage distortion in your plant. So our recommendation generally is if you have drives in the plant, even if they're active front-end drives or high post drives, install some type of filter into the network or a detuned cap bank. And that's going to be the topics for next week, is how these devices help you out. Just a couple more topics today, and we'll be closing up. So remember, I expanded that network again to include both the secondary bus and the primary bus, followed by the source impedance. Depending upon where you are in the network, you have what's called parallel resonance, or you have series resonance. So looking from the load here, it's a parallel resonance. This capacitor is in parallel with this impedance here. But looking from the transmission side, the source side of the transformer, you have both a series resonance here, and then also a parallel resonance, which would be this impedance here in parallel with this impedance here. So you have a parallel resonance. So you get these two different curves. So this is particularly true for systems that might consist of 4160 volt systems, as well as, oh, we got a question.
Yes, Paul, you have a question from Christian. He says that the model used for power grids doesn't take into account the capacitances upstream. The PCC, when fails to model the frequency response of the grid, is this a proper model for harmonic analysis? Maybe the effect of grid capacitances is negligible. Is there a better way to model this?
Well, it's a good question. First of all, there is capacitance with that transmission grid, and the question is, does it impact the model? And really, when you're doing a harmonic analysis, you have to determine, okay, does that impedance of the source, that transmission grid, is modeling it as a straight reactance, as I've done here, is that adequate? Or should I be doing a more complex model? And that really becomes a question, how far back into the transmission grid do you model? For the most part, most companies are modeling that source impedance as a reactance. If there's a capacitor bank there, you of course have to say, well, is that capacitor bank on the transmission level side, transmission grid side, is it going to have an impact on the source impedance? And if it does, then you have to model it. So normally I do a sensitivity analysis. I ask the question on the transmission side, do you have capacitors there or not? What does the transmission system look like? Does it make sense for me to model back to the next substation to capture that impedance? Maybe most of the harmonic analysis programs are doing a pi model or a long transmission model, and they're capturing that capacitance of that transmission line. Does it make sense to capture that? And a sensitivity analysis is what I would do there. I would look at the two impedance curves, one with it modeled, one with it not modeled, and make that determination. With that being said, though, we had a tech talk week before last with BBA, and Hydro-Quebec does an impedance loci. So they're modeling a range of frequencies and capturing more of the possibilities of impedance changes on the transmission level. But there's really no rule of thumb here. The objective here is you're doing harmonic analysis. You're trying to calculate really what is the current distortion at the PCC here, what is the voltage distortion at the customer's loads, because power quality is really the primary concern. And if the model of the transmission system isn't representative, your results will be wrong. So you have to do some type of sensitivity analysis and determine what makes sense, and do you need to model more there. But for sure, capacitance on the transmission system can have an impact on your results, and it's important to always think about low voltage capacitors. If I have 480 volt capacitors and I'm putting in medium voltage drives, you should be looking at low voltage capacitors because they're going to create what we show here, series resonance. And you should always also be looking at the transmission level capacitors. What, if any, can have an impact on your system? So a very good question. And I like the new format. So the end result here is we were talking about low voltage capacitors at the 480 volt level and medium voltage capacitors. So when doing power factor correction, it's often thought, okay, I'm going to place capacitors at the load. So the philosophy oftentimes is to put capacitors at the 480 volt level, at the 4160 volt level, and even at the 13.8 kV level. And the result here is that you create a very complex impedance curve. You have series and parallel resonances throughout the network. And I say from a designer standpoint, it makes it very difficult to determine the power quality of that system and what the resulting voltage distortion will be, partly because normally there are multi-stage banks here, and the number of iterations required to do the analysis gets to be enormous. Sometimes you have main-tie-main systems, these redundant systems, and you have to open the tie and close the tie, adds to the number of cases. And then you got low voltage capacitors, which are on and off based upon motors. So our philosophy here is you should pick a load level to do your power factor correction and keep all the capacitors at one voltage level and determine should those capacitors be harmonic filters or should they be capacitors. So I kind of have this curve, and I just stole this off the web. But impedance curves can get very, very complex. And if you do a harmonic analysis and you get some type of impedance curve that looks like this, your impedance scan looks like this, it's very difficult to fix. You're lost as to, well, what's causing the resonance and how do I fix it? So the easiest way to get a grip on your analysis, on your results, is to try to minimize the number of capacitor banks you have in your network, and that will help you control what's going on. So we recommend correcting power factor at one voltage level. So multi-stage banks, just to kind of touch upon this, we set up our system for a 1, 2, 3, 4 megavar system, and we do the same type of analysis. I take that impedance and all those possibilities. I have 4 possibilities. Technically I have 5. I got the straight transform impedance line, and then I have a 1 megavar, 2 megavar, 3 megavar, 4 megavar impedance scan represented by those colors. And you can see that I have an issue with harmonic voltage at the 11th harmonic because of the 3.8 amps of current injection being multiplied by this impedance when I have a 1 megavar stage on. I also had this problem down here originally with the 4 megavar bank on, that I was concerned about the shift there. And of course with this blue line here, you would also have a concern maybe it would go over the top of the 7th. So I would see this as a system that potentially could be problematic. And the results would be a very high voltage distortion. So in this case, we would consider detuned banks or even a tuned bank at the close to the 5th harmonic. And we're going to be talking about that next week, why that benefits you and what it does. So what happens during resonance? You get current amplification, you get voltage distortion also, we talked about that, but you also get current amplification. In the capacitor bank itself, you can see here what I did, I inject 1 amp of harmonic current at each and every frequency in the network, and I then measure the current flow in the capacitor or in the source. It's the same thing at that point because it's a tank circuit. And I measure, okay, well, what is the current amplification? So for 1 amp of injection, you can see that at this frequency, I could get up to almost 80 times. And this is why when you have harmonic resonance, capacitors blow their fuses. They blow their fuses because the current is amplified. We size the fuses at roughly 2 per unit of the capacitor current. Here you can see that we're multiplying our harmonic current by 80, so it's very reasonable that you're going to get to a point where you're going to operate your capacitor fuses. So almost in all cases, from somewhere below the tuning point or the resonant point of the system, all the ways up to higher frequencies, I have current amplification. And this is key here. I'm going to go to the next slide and show you what that means. It means that the current amplification is amplified here and here. It's actually amplified at the point of common coupling, which is on the transmission side here, and it's also measured here. And it's shown over here. We have our harmonic current injection here, and the amplification factor is amplified there. So we get this much higher current. So
Paul, you have another question.
Okay.
Normally, grid is supplying max and minimum fault level and the X over R ratio. Beyond that, they're not providing any additional information. However, grid code does provide with voltage harmonic guarantee. How can we?
Okay. Normally, the grid supplying. Okay, so you got to do harmonic analysis for min fault current, maximum fault current. If you have no other data, then your analysis is based on that data, of course. But you can ask questions about the transmission grid. How many miles to the next substation? Try to capture some of that capacitance, say, associated with the transmission line. But you're trying to do the best you can. And then with voltage harmonics, is very difficult to, and I think what you're getting at here is how to take care of ambient voltage distortion. Generally speaking, I do the analysis assuming 0 voltage distortion on the transmission grid, and my primary concern is, well, what am I as the industrial customer, or if I'm doing a study for the industrial customer, what am I producing for voltage distortion in my plant, and is that result going to be an issue or not? And I'm shooting for 5%. So you can have a situation where the voltage distortion out here in the transmission grid might be 1%. And I do see some people that go to the IEEE values and they'll assume the voltage distortion to be that value, okay, as an ambient. And that actually leads to a very conservative result. And the reason being is a voltage source out here in your model. The question is, what is the impedance behind that? How much current can it drive? And remember, during series resonance, it can appear as a short circuit. It's basically a tuned filter. The transformer impedance with the capacitor forms a filter from the transmission grid, and it could create a very high current draw. So modeling voltage distortion out here is a difficult task, actually knowing what to do and how to do it. So we typically stay away from doing that. Most oftentimes I don't see studies assuming a value there because you don't know the impedance behind that voltage source. So remember, normally we're dealing with harmonic current injection creating voltage. And then it's that voltage that we're concerned about. So my question would be, if I have voltage distortion out here, what's producing that voltage distortion? I would want to figure that out and maybe model that as a current source at that point or location where that load is being applied. And that's not something you always know. Most often you do not know it. So it's kind of like, I always say it's like a dead battery. If you go to a dead battery and you put a voltmeter on it, you measure 12 volts. But if you try to start your car, it doesn't start. And that's because there's a lot of impedance behind it. It can't deliver the current. So the point with this slide that I wanted to make is that this capacitor bank here, okay, is causing the amplification of current in the network. And the point of common coupling, remember, is out here. So the point of common coupling is in the path of current amplification. So Adding a capacitor to a system can easily cause a system to exceed IEEE 519 requirements. So you got the concern of resonance, you got the concern of exceeding IEEE 519 at the PCC, and that's really the two concerns with adding capacitors. So the word of caution here is when adding capacitors, consider the impact of resonance on the system. Is it going to cause problems? And then the other thing that's interesting with this slide is oftentimes a customer will have a voltage distortion problem or current distortion problem, some type of power quality problem, and they send a guy out there with a meter to take measurements, and they'll put the measurement device here to measure current and voltage distortion. But they'll leave the capacitor bank on. And this is an issue if you're trying to do harmonic analysis and you're trying to capture this piece of data right here. You want to know, well, what is my current injection? Because you want to do a what-if analysis. Okay, if I know my current injection, I can put the capacitor bank on and try to replicate what's going on in the system. You have to tell this customer to turn their capacitor bank off. Otherwise, the data that you capture here is not this data, but rather that data here, which is an amplified value. Very often I get harmonic measurement data. My first question is, are there capacitor banks on the system? They answer yes. Then my next question is, did they turn them off? The answer is no, and to the most part, they wasted their money. You have to turn capacitor banks off, even if it's for 5 minutes. It's the best piece of data to do harmonic analysis, is to actually turn that cap bank off. Okay. So I was going to do this question, but we are over the 1 hour mark, so I'm going to hold off on this question. I think next week we will start with this question. We're going to actually go to a whiteboard. I want to show you how it's going to work because it's something pretty cool. I have a whiteboard here, and we're going to go through the problem like this. So we will go through how to calculate this, and you can kind of see how it works. We'll go through a couple of different ways I do it, but for the most part, I can pick up a calculator on a system like this, and I can immediately calculate the voltage distortion at this point very easily. And I want to show you guys how I do it. There's a couple different ways, but it's a pure calculation. A lot of times you see the low voltage capacitor suppliers coming up with rules of thumbs, harmonic penetration percentage of secondary load. I say forget all those tables. To some degree they're baseless tables, and actually go back and do the calculation because it's very easy to do. By assuming just this data here, by assuming the impedance data and doing basically Ohm's Law. So we're going to skip that for this week because we don't have time. So next week we will talk about how to do that calculation, and then what harmonic filters do for you, how they correct this issue of resonance, and how filters help improve power quality on the system. And we'll basically step up from where we are to adding 4 single-stage capacitor banks as standard cap banks to actually add those capacitor banks as harmonic filters, and we'll talk about how those filters work. So PDH credits for today is 321. Just send us an email if you want some PDH credits. And in conclusion today, harmonic analysis is not that complicated. It's an extension of Ohm's Law. If you're using a harmonics analysis program, I say that you have to be able to take a simple system, do the calculations I show here, and compare them to the output of the harmonic analysis program. You have to be able to do that because if you can't do that, you can't trust the results of the harmonic analysis program. The analysis program is a tool to simplify the calculations. It's not a replacement for knowledge. And that's really the key here. We oftentimes see the analysis tool in the hands of somebody who's not knowledgeable. So you want to be able to go back to the calculations here, do the calculations, confirm it against the harmonic analysis program, and and we're going to talk about this next week, as you are validating your model, you're doing these types of calculations. You're trying to say, hey, does it make sense what I'm seeing? Does it make sense, my current that I see here, does the voltage distortion make sense? And you're doing validation type problems, as we are going to show in this problem next week. You have to do some type of validation Otherwise, your results may not be correct. We're going to be talking about that next week more. And the other thing is when adding capacitors, consider the impact of resonance. Even if you have AFE drives, or I would call harmonic IEEE 519 compliant drives, if you're adding capacitor banks to the system, you need to consider resonance, because resonance will still cause problems even with low-level harmonic current injection from the drives. Okay, so.
We did have one more question if you want to take that.
Yeah, we'll take that question.
Okay, so this last question from Volt, isn't there some rules of thumb that you should not have to do the analysis if the capacitor amount in kVA is less than 20% of the system kVA source?
This is exactly what I was talking about. The rules of thumbs. There is no basis for those rules of thumbs. I can easily show you that this 20% rule does not work. If you have resonance, you got a problem. It has nothing to do with a percent of load. I've been seeing this, and this is really something produced by the low voltage guys. If you have harmonic current injection, even a very low level amps, remember that one curve I showed an impedance of 500 ohms, just 1 amp into 500 ohms creates 500 volts. At the 13.8 kV level, that's already too much voltage distortion. And the same happens at low voltage. You could go through the calculations. You can calculate what resonance might occur, what the ohms might be, and you can easily see that even a very, very low level harmonic current injection into that impedance is going to cause a high voltage distortion. And in general, you want to design a system so that you have less than 5%. So those rules are really baseless rules. I was in the low voltage industry back in the early 90s when they were developing those tables, and they were basically developed by the marketing people, not by the engineers. And I remember having arguments about those tables. Really, there's no ground basis for those rules. So next week, we're going to continue our discussion. We're going to talk about harmonic filters, how it impacts the impedance curve, why you want to apply harmonic filters or detune cap banks. We're going to talk about that concept too. We'll bring up the three major types of filters, high pass, C-high pass, and notch filters, and really the differences between those filters. And remember, the primary reason for installing harmonic filters is not always harmonic filtering. Number one reason, reactive compensation. Number two, prevention of resonance. Number three is harmonic filtering. And then four, sometimes preclusion of resonance. They are the four reasons why you install harmonic filters. So unless we have more questions, we'll close up the shop for this week. Remember, NEPSI is a manufacturer of metal closed cap banks, filter banks. If you have a project, we would be happy to work with you and also develop that project with you. We have a significant amount of information on our website, guides, form specifications, how-to videos. If you go to our YouTube playlist, this is now number 17. Which is amazing, and you'll find lots of information there also. We have case studies, spreadsheet tools, calculator tools, so all kinds of information. And of course, reach out to NEPSI, sales@nepsi.com, or myself, and we'll help you develop your project. Thank you for watching.